Good morning to everyone. Thank you to the Flight Software Workshop Committee to give us this opportunity to present our work. Well, my name is Gaston. I'm from CONT'n, that is the Argentine Space Agency. I am an engineer that I worked with the software for a payload on the SABIA Aquarius mission. And I'm here with other members of the team, that is Roberto Alonso, who is the mission system engineer of the SABIA project, and Jose Cuba, who is the mission analyst for the same mission. And I want to mention another member of the team, that is Nadia Pucci. She was a master student who worked with us as part of her master thesis. Okay, next slide, please.
Okay. Yeah, I switched the next slide immediately, but it's going to take some time for you to see that on the YouTube. So you just proceed after 10 minutes, okay?
Okay. Well, we are going to present an overview of a concept to change the way the mission planning is done today. These are the sections of this presentation, and in particular the applications to LEO satellite and extension to Constellation. Those two sections, they are going to be presented by Roberto. Roberto is the person who starts with this work. Okay, next slide, please.
Okay, I'm on slide 3 now. Current mission architecture.
Okay, yes. Here is just an introduction to show you how the communication between the mission center and the satellite is done today. Regarding to the planning, the mission center configures the plan, generates the telecommands, and then send that set of telecommands to the satellite. And for the mission centers, it costs around 90% of the contact time to send those amount of telecommands. So the satellite finally only executes those commands. Please, next slide.
Okay. Next slide.
Okay. Here we have the motivation for a change to this way the planning is done. So we know that today the hardware has evolved, and we currently have enough onboard processing power to let us add new functions to the software. For example, we can now, if we want, we can add some functions to onboard image processing and also onboard mission planning. On the other hand, for countries such as Argentina, we have very little contact time, so we need to optimize that time. And the idea is to reduce the amount of telecommands that we must transmit from the mission center to the satellite. For example, if the mission requires adding new areas of interest for the mission, the idea is that now we want to add these new functionalities in the flight software, and our first step is to implement an autonomous onboard mission planning. Next slide, please.
Okay.
You are in number 5 page?
Yes. Number 5.
Okay, well, this is the proposal, is to change this parameter to the mission centers, just monitor or supervise the automatism in the satellite. Well, the satellite will generate the actions to accomplish the mission plan. Next slide, please.
Slide 6.
Okay, well, these are the main functions for the planner. I want to mention something from here is that the idea of the planning is to use something that is called a polytope, that is like a polygon, and we'll use this information to generate events when the satellite is passing over that area. The polytope is a set of points that will define a closed area in a convex, like a convex polygon. Each point is defined with latitude and longitude value. And in our planner, the polytope will represent the area of interest on the surface of the Earth. And so when the satellite is passing through this polytope, you can link different actions, different commands, different scripts to be executed in that moment. Next slide, please.
Slide 7.
Yes. Here, well, we have another functions of the planner. Well, the planner will need to determine different information from the satellite, that is the position and the altitude. With that information, the planner must determine what we call subpoints. That subpoint, for example, the subsatellite point is referred as a point on the Earth's surface that is linked to the nadir vector. And then you can have another subpoint, like for each instrument you have on the spacecraft, and each subpoint will represent that instrument on the Earth's surface. So the idea is that the algorithm that the planner will execute on board will determine the position of these subpoints respect to the different polytopes you have on your list, on your in your mission plan. So when these points enter the polytope, the software will generate different events. Next slide, please.
Okay. Calibration area.
Yes, this is an example of a polytope on the surface of the Earth. Next slide, please.
Okay. Geometrical view.
Okay. Well, here you can see a polytope and 3 subpoints. Okay, you have one satellite point, then you have 2 as an example, sub-camera points. 2 subpoints are inside the polytope and will execute an event that is related to that position, and you have a subpoint outside the polytope, and that point will generate another event related to that position. Next slide, please.
Okay, closer
I'm
view.
going very fast for this.
Mm-hmm.
Okay, this is a closer view of the geometry. Here we define 4 events. We call it go in, the event when the subpoint that's the first step inside the polytope. Then you have the go out, that is the first step outside the polytope. And then you have the inside, that are events that when the subpoint is traveling inside the polytope, and then you have the outside event. Next, please.
The box.
Okay, this is not a box around it. The polytope is a square, and on the polytope, that's a mistake, sorry for that. And this is just an optimization for the algorithm that to avoid execute all the process to check if the point is inside or not the polytope. It will use the minimum and maximum latitude and longitude values of the polytope. So when the subpoint is inside that area, the software will start processing the algorithm. The algorithm that we are using is based on the Jordan cube theorem that this theorem, this algorithm, just calculate if any point is inside or outside the polytope. Next slide, please.
Okay. First version.
Okay. Yes, this is just to start the idea of how we are developing the software. The idea is that the software is going to be like a library, and we don't want to be fixed to an operating system, so the software will not have any system call. And, well, the software must have this functionality, trigger events and alarms, generate reports and telemetry, and execute commands and scripts. Next slide, please.
Okay. Software design.
Software design, where this is another functions, and here the most important one is the last one that says the planning table has two operating modes, real-time and time tagger. The idea is that this software can work in real time, that is always doing the processing if the subpoints are inside the polytopes, and then executing the event, or a time tagger mode that I will explain in the next slide. Next slide, please.
Okay, the simple approach.
Okay, the time tagger mode is very similar in what the mission center today does for generate the planning, the mission planning. But in our case, because the software is going to be executed on board, the software needs to have functions to propagate the orbit, for example, for today, and we generate a table with all the points where the satellite or the subpoints, the instrument subpoints, crosses each polytope. So we generate this table, and the software will mix this information with the mission planning table, and will generate the time tagger planning table. That is a set of actions with the time to be executed. Next slide, please.
Okay. It's the continuation slide.
Okay, here is just an overview of the blocks. These blocks represent the modules for the software, and that module handles different functions for the planner. Here you can see the Jordan block, that is the function that calculates the subpoints and the polytopes. Next slide, please.
Thank you. The advanced design.
Okay, well, this is related for the orbit part of the planner. The planner needs to process some information from the different sensors that the spacecraft has, and with extra information we generate that output data that are the filter orbit and other information that the planner will use to generate the subpoints and to do this event predictor and time target tables. Next slide, please.
Okay, the baseline.
Okay, well, this is the basic design for the satellite, and regarding this planner, we are going to have the first stage of the version with some restriction, and this first version is going to be included in the software of a payload computer in the SABIA Mar mission. So now I will let Roberto explain this part.
Okay, hello everybody. SABIA Mar mission is an ocean color mission from CONAE and also for the Brazilian Space Agency, and it's a sun-synchronous orbit, 9 days of revisiting time. We have on board 3 main cameras covering from the ultraviolet bands to the thermal infrared, and some part of the mission is performed during the ascending orbit and the other descending orbit. So there are a lot of scenarios. There are a lot of. We are in the slide 18. I'm sorry.
Okay.
In the SABIA Mar mission case. I'm sorry for.
No problem. So I'm on slide 18 now.
Okay. This is the shape of the mission. The mission is starting the CDR next April. So we have most of the studies finished. Next slide, please.
Okay. Simulation slide.
This is a simulation of the SABIA Mar orbit, where we have a polytope, the orbit, and the sub-satellite point that with the field of view is a large field of view of this satellite. So is to show the position of the sub-satellite point with respect to the polytope. Nothing more than that simulation. The planner has to provide us the possibility to use also just to study the allocation of memory, the contact time. There is a spin-off also from the mission design. Next slide, please.
Slide 20, Constellation.
Yes. 20. The extension of this idea to using the polytope on Earth was to simulate the possibility to have the constellation tuned from the idea that from CONAE has a constellation of 4 satellites. The first approach was to cooperative satellites between the master and some slave, just as an idealization with some ground polytope. Both of them are working and sometimes cooperative with the mission. The idea is to have the master satellite has the less amount of information with respect to the other satellites to maintain the configuration. It's not important the absolute configuration, just the relative configuration for our needs. We will extend then the idea for absolute configuration. The space polytope is created from each the satellite that should be involved in the constellation. Next slide, please.
Okay, that's continued. I'm on slide 21.
Mm-hmm. We use the same idea, the same algorithms. We try to avoid the formulation, the mathematical formulation here, but we have all the algorithms ready with the master satellite to use the same idea of entering and leaving the polytope to understand when it's necessary to perform orbit calibration for the relative architecture between slave and master. The same ideas that we use for Earth that is implemented on SABIA Mar and is the baseline for the software. I forgot to mention that this planner is already on board of the computer for SABIA Mar in the payload section, and is the baseline for working with the cameras. We try to avoid the amount of time-target command because, as Gaston explained, our contact time from the ground station that is in the center of the country is very small. So we plan to have only the task of monitoring the automatism of the satellite. The extension of Constellation is for the next satellite, the next mission that is a constellation of 4 satellites. Next slide, please.
Okay. Yeah, summary.
The summary, Gaston will explain the summary.
Okay, well, sorry for the mess. We talked, I think, too fast. Well, the idea was to show you a general view of the concept for our autonomous onboard mission planning system. I don't know if you understand something. So, to conclude, well, the mission center changed its role from being the activator of the mission to just supervise the actions of the onboard planner. And then the mission plan became like a dynamic document where changes are easy to make, and the addition of new polytopes should not generate an extra effort in the control center. So if there is a new area of interest for the science people, they only need to define the polytope and then the actions to execute for this polytope or area of interest. So the mission center will send the command to configure and to add this new polytope to the planner, the onboard planner. That's the idea. So next slide.
Questions?
Thank
you very much, Gaston.
Thank you very much.
Thank you very much for